Hello, welcome to another video, and the second unit of physics, and I'd argue the second unit of physics 1, and I'd argue this is, probably the most important unit of everything we'll do in this class. I guess energy has its uses as well, but this really is the cornerstone of physics 1, I'd say. So this lecture is going to be about Newton's laws of motion. So let's look at why we're doing this. So for, in Unit 1, what we looked at was the motion after forces have been applied, right? So we looked at, like a ball already kicked. Okay, so it's already kicked, or some jumper already not leaving, jumping off a cliff, right? So you looked at stuff that already happened after the fact, and then you examined that motion, right? That's what we were interested in. We examined the ball flying through the air, so ball in air, and we looked at the motion, right? So here's the motion. That's what we cared about, or maybe the guy jumping off the cliff, okay? So we looked at the motion. That's what we cared about. But now what we're going to do is we're going to examine the forces themselves. So we will examine what happens before the motion, and then we'll maybe apply it to motion afterwards. Okay. Let's go ahead and to start this, basically, there was a guy, Sir Isaac Newton, okay, and he created these laws of motion, is what they're called. So let's examine Newton's 3 laws of motion. And these will tell us the before, okay, or the cause of motion. Okay? So the first law of motion, and they're just called, Newton's first law of motion, Newton's second law of motion, Newton's third law. But the first law of motion, what this guy states is that a body, this is, an object, okay, at rest, and we'll define what that is, will remain at rest unless acted upon by a net external force. Okay? So a body at rest will remain at rest unless acted upon by a net external force. So before we kind of can digest what this even means, we need to define some stuff, okay? So first, let's define at rest. So some key definitions here. So at rest, what does this mean? This means that a body or object, however you want to call it, is in equilibrium. Okay. So now, what does equilibrium mean? Equilibrium, this means that all forces acting on an object, cancel out, okay? And or just, not really and, just or result in a net force of 0, okay? So when an object's in equilibrium, there's some number of forces or no forces of all, or there are simply no forces acting on an object, okay? So there's either a bunch of forces or there's no forces at all, and they basically cancel out on an object. So if you have a force to the right, there's an equal force to the left, okay? And this state, so equilibrium, can exist in a static state, so like the object isn't moving, or a dynamic state, as in the object is moving, okay? So what this means is you can be in equilibrium and be moving. It is possible, okay? Theoretically, at least. Potentially on Earth as well. But you can also just be not moving at all. And you will be at equilibrium, okay? So what else? So that's at rest. That means you're in equilibrium, okay? Now let's define net. So what net means is the total amount, okay? In this case, referring to forces. So the total amount, in this case, the total amount of force, okay? So sum of force, so the sum of the forces, okay? The sum, okay? What else? External, okay? External just means outside the object, okay? And now force, I will go ahead and define as well. A force is just an interaction, okay, between one or more objects, okay? You can also think of this simply as like a push or a pull, is what a lot of people just think of. If you're interacting with some object, right? Like I pick up my phone, I'm interacting with it. I'm applying a force to it in a particular way to interact with it, okay? So now let's reread that sentence again. or reread the Newton's first law of motion. So a body at rest, oops, can't draw. A body at rest, meaning a body in equilibrium, in that special state, will remain in that special state of equilibrium unless acted upon by a net external force. Meaning, ultimately what this means is objects keep doing what they were doing before a force is applied. Okay? So my phone, i.e., my phone will continue to sit on my desk unless I interact with it. Or another net external force does. Okay? Meaning, if I do interact with it, if I interact with it also with another force that cancels that interaction out, then it will still be in equilibrium. Okay? So you have to interact with it in such a way that you disturb that equilibrium. Okay? So equilibrium is a special state. Okay? Where the net forces sum to zero. Okay? So you can think of this as the law where it's before the motion or before the force is applied. So first law is really just discussing before net forces are applied. Okay? So now let's talk about Newton's second law of motion. So the first law ultimately isn't too interesting. It's not, there's really only a couple cases, really only a couple problems where you can work with that. It needs to be said nonetheless, but the second law of motion is really where it's at, okay? So the acceleration of an object as produced by a net external force. So now the second law is discussing what happens when you have a net external force, okay? In other words, it's not zero or sum to zero, okay? So the acceleration of an object as produced by a net external force is directly proportional to the magnitude of the net external force. It's also in the same direction, because they're both vectors, as the net external force. And it's inversely proportional to its mass, okay? Or to the object's mass, okay? So let's look at this. Let's read it one more time. The acceleration of an object as produced by net external force is proportional to that force in the same direction as that force and inversely proportional to its mass. Mathematically, this is what it looks like, okay? So the acceleration of an object is directly proportional to the force. So if the force goes up, the acceleration goes up, and it's inversely proportional to the mass of the object, okay? This is more famously written as this, okay? This right here is sigma, and this denotes the sum of the forces. So this means that this would have I number of forces, okay? So the I denotes forces up, forces from 1 to n. In other words, some arbitrary number. You can pick however many forces are acting on the number, or on the object. Are there 10? Then it would be force 1 plus force 2 plus force 3. So here, let me write that real quick. So, i.e., I equals 1 to, let's say, 3, okay, of Fi. This is shorthand for 1, 2, plus 3. You just replace the I with the value 1, 2, 3. Okay, from 1 to 3. And then on the right you have the mass of the object and the acceleration of the object. Okay. You may also see this written as, so what you do is you take this guy, and instead of acceleration, you plug in what acceleration is, which is the rate of change of velocity. And then you can move the delta to the outside and allow mass to change too. Okay, so the mass of objects could change. And then you get this new thing right here, mass times velocity. And so what you can do is you can write that as a new quantity as well. Delta P, okay, is what that's called. And this is momentum. Okay, and we'll talk about this in Unit 3. So this will be in Unit 3. Okay, we'll talk all about momentum. But momentum is also directly proportional to a force. And you must be wondering, well, why would I want the mass to change on an object? For like a rocket ship, right? So as like the rocket goes up in the air, it's ejecting more mass out the bottom, right? It's ejecting its fuel, so its mass is changing. And that's producing a force, right? So yeah, that's why you would use that. But definitely, by and large, F equals ma is the most important thing from this. So by and large, F equals ma is the most important form for us. This equation is so valuable, okay? This is probably the most important equation in the entire class. Because from this equation, you can derive so many other things. This equation is where kinematics actually comes from. You can derive the kinematics equations from this. You can derive other equations of motion from this when acceleration isn't constant. Okay, it's super important. So know this equation. Okay, it's extremely important. Okay, it's also an axiom. You know, I can't mathematically prove that this equation is true. It's just shown to be true through experiment. Okay, so this, you know, it's only shown to be true through experiment. You can't mathematically derive F equals ma. And so everything else kind of stems from that. Okay? All right. So how can Newton's third law of motion live up to that? Or the first law, really. It has its own uses. So Newton's first law was really before there's a net external force. Newton's second law is what happens when there is a net external force. Okay, so before a net external force of 0 and then a net external force of something. Okay, this guy is what happens to the object that's doing the interaction with it. So this is whenever one body, right, or object exerts a force on a second body or object. Okay. The first body experiences a force equal in magnitude and opposite in direction to the force it exerts. In other words, anytime I interact with something in this universe, that something interacts back. I touch my phone touches me. Earth pulls on me gravitationally. I pull on the Earth gravitationally. Those forces are the same. Okay? Even in the case of large forces, like Earth pulling on me with this massive gravity, the force I exert on the Earth is the exact same. What changes is the acceleration of that object, right? Like, it doesn't affect me, or I don't affect the Earth that much because it's got a huge mass, okay? And so mass you can kind of think of as the resistance to force, okay, in all of this. Okay, so mathematically this force then F on A, or here, let's do this. F on B by A equals the force on A by B. So let's look at this. You have a box, and you have another box. This is box A, this is box B. Box A pushes on box B. This is the force on B by A. In doing that, B exerts an equal and opposite force in the other direction. This is the force on A by B, and they're in opposite directions. Okay. This is known as on-by notation. In other words, what this means, it's the force on A by B, okay, equals FAB. By and large, most books, most textbooks, we all kind of use this notation. And so that's kind of what it is. You may also see this equation with a minus here to denote direction in the opposite direction. But because of the way, like, you may see it with or without. It just kind of depends. As long as this right here, this guy kind of denotes the direction, right? Because it's on A by B. And so if you have that there, the subscript will denote direction. So you don't need to add a negative here. But yeah, that's kind of what third law is. So in short, let's just first law, net external force of 0. The second law is net external force producing acceleration. Okay. And as F goes up, A goes up. As mass increases, A decreases. Okay? And that's because mass is a quantifiable measure of an object's resistance to force. So if an object has more mass, okay, it's more resistant to force than an object that doesn't have mass, okay? And it's a quantifiable measure of that, okay? And then the third law, so second law is the most complicated. So the third law is what happens to the object exerting that net external force. Okay. It's the result of what happens to that guy. Okay. So if it exerts a force, it gets a force back. Okay. So i.e. a force is exerted back. Okay. So let's define some more stuff. So we need to talk about force, okay? This is the most important term in this section. So everything we do will involve force, okay? So let me redefine it, okay? So again, this is any interaction between two or more objects in the universe, okay? And, you know, push or pull, okay? It is a vector, so it has magnitude and direction, and it is a vector also because it is defined in terms of one, acceleration, okay? There are 4 fundamental forces in the universe. So there's 4 forces that breaks down into all the forces that we interact with and do and are able to perform things daily, okay? They're varying strengths, okay? So 4 fundamental forces of varying strengths. We've got gravity, Okay. We've got the electroweak force, also called the weak nuclear force. We have the strong nuclear force. And we have the electromagnetic force. Okay. I believe the order of strength is that, let's move that guy down, let's move this guy, is I think it goes like this as far as strength. So this is increasing strength. So gravity is actually the weakest force. The only reason that it has any any bearing at all is because the objects in our universe are pretty massive, right? Stars are huge. And you know, you have other stuff too, right, with lots of mass, like black holes and things like that. I think it's also called the weak nuclear force, so I'm just going to rebrand it as that. The electromagnetic force, you know, this is basically, these two are what we interact with daily, and then because this guy, the electromagnetic force, will break down into like friction, our sight, how we touch things, and then, of course, gravity, just because we're surrounded by the Earth and other massive objects. The weak nuclear force and strong nuclear force hold like atoms together. Okay. So those are the 4 fundamental forces. And these 4 forces, like I said, break down into forces we deal with daily. Okay, so like I said, this includes, you know, friction, touch, sight. You know, these are derivatives of the EM force. And then, of course, gravity, right? We interact with all the time too. Forces can also be divided into contact and non-contact forces. So again, this would be like touch, friction, etc. Non-contact, an example of that would be gravity. Okay. But you also have things like, you know, in physics too, you would have the electric force is non-contact. Magnetism, or the magnetic force, is non-contact. Okay. And these guys interact with fields as the mediator, is how they transfer the force. Okay. But for us, for contact forces, this is, you know, most of physics 1. Plus gravity. Okay. Let's talk about the SI unit of force. So the SI unit of force is named after Sir Isaac Newton, right? So it's the Newton. Okay. And 1 Newton, symbol N, is 1 kilogram times meter, kilogram meter per second squared. And that's because F equals ma, right? So kilogram is the unit of mass, unit of acceleration is meter per second squared, and so the Newton is a combination of those. Like I said before, in, I think, the first lecture, everything in the universe can be divided into those base units. And then you can derive more units from that, which is what we've done here. Okay. Okay, so that's kind of everything about force. Now let's talk about Newton's second law in more detail. So Newton's second law, by and large, is the law we will focus on, okay, in this class. Okay. And so to do this, so to utilize this force, or this law, we need to sum the forces on objects, right? Because if you remember, the sum of the forces, right, from I equals 1 to n equals ma. The problem is, right, each of these forces that you add are vectors. So the forces we need to do vector sums. Okay, we need to be able to add this vector plus this vector, right? But luckily, we did that already, right? So we've done that in Unit 1. And so we'll continue to do that here. That said, there is a methodology about how to add forces, okay? And step 1 is to draw what's known as a free body diagram. Okay? And this is abbreviated as FBD. Okay? So anytime you see we're going to draw an FBD, that's a free body diagram. So what is a free body diagram? It is a visual representation. That is a long word. It is a visual representation of forces acting on an object. Okay? So let's look at how this works. Okay? So here's the situation. Okay, there will usually be different situations for objects. Let's just say my phone on the desk is the situation. And we want to diagram the forces on that phone. So we want to diagram the forces on the phone. So step 1, draw the phone as a dot. Okay? Phone is drawn as a dot. Okay? Step 2, add gravity. Okay? So gravity will pretty much be present unless explicitly told not to in every single problem. So we always add it. Now, here's where I kind of differ from other people. You may see gravity labeled as just a G, okay? What I do is, because it's the force of gravity, I always draw an F subscript G, okay? That's just how I've done it for who knows how long, okay? So you draw the force in the direction, and then you label it, okay? You don't have to use this notation. You can use, you know, like I said, I see textbooks that do G all the time. You can do that, okay? That's up to you. So then step 3, once you've done gravity, is add other forces, okay? And so here's a list, starting with most common and working their way, I guess, up, okay, to less common or more situational. There's something called the normal force. This is abbreviated how I do it, Fn, but you may see N, okay? And this exists when an object is touching a surface and acts perpendicularly into the object from that surface. And this is also called normal to the surface, okay? So for example, for my phone on the table, it's touching the table, i.e. phone on table or desk or whatever. So it's touching the desk. It points up, perpendicular, and I would just label it like that. Because here's what the phone looks like, right? So the phone's just sitting on the table. The normal force acts perpendicularly upward into the object, okay? And this is, again, normal to the surface because it forms 90 degrees. And so that's why it has the name normal force. There's also tension is another force, okay? This is F of t. You may also see just T. And this exists with non-springy strings or ropes are present. Okay, so for example, a sign. Here's the sign. You know, maybe it looks like this. I think this is an example for us. Your FBD for this guy, you have 2 ropes right there and there. It would just go like this. And of course you'd have gravity as well. Okay, so it would look like that. You've got friction. Okay, we'll do friction in a later section, or not a later section, just later after we do a bunch of other examples. But friction exists. Oh, here's how you abbreviate friction. there's static friction, and there is kinetic friction. Okay? For if an object is moving with kinetics, so this is moving, or if it's not moving. Okay? And so friction exists with, rough surfaces. It's very, you'll see in problems, it's very explicit when there's friction. It acts opposite to the motion, okay, of the surfaces of objects, okay? You'll see what I mean by this when we do friction more explicitly. You have push, pull, so these are like generic pushing or pulling, and they'll be like in the problem, right? It would be like a man is pushing a lawnmower, okay? Something like that. Some guy is pulling a box. The way you see these abbreviated, it could be FP, it could be P, it could be maybe F1, F2, etc. Okay, and these are specific to the problem. Okay. So for now, like I said, our the phone is just going to look like this. So here's our phone free body diagram. Okay. And then you look through, is there anything else? Is there friction? No. Is there tension? No, there's no ropes. There's nothing like that. So, yeah, that's pretty much it. These are most of the forces. I guess there's technically also springs you may see. We don't do springs often. This mostly comes around with energy. So we'll do it when we talk about energy. And that's why I set up here with the tension. It's non-springy strings or ropes. But it is, I guess, possible to see this here. And I guess springs would be abbreviated maybe SP or something like that. Yeah. So step one to solving these things is drawing the free body diagram, okay? So, and you use those forces to do it. So, step one to solving with Newton's second law was drawing the FBD, okay? Step two is creating X and Y equations with the FBD, okay? So for example, what we've got so far as this, so for the X equations, there aren't any. If we have a typical coordinate system, there aren't any forces in the X. No X forces. And there's only Y forces. And since we defined Y as up, we would say Fn minus Fg equals 0. Okay, and this would be our equations for this. I'll go into more detail about how step 2 works. But step 2 is literally sum of the forces equals ma. And the reason this is 0 here is because for this particular example, the phone's not accelerating in the y. And so this would just be 0. And so the sum of the forces equals 0. Okay? And there aren't any x forces. And then step 3, solve. Okay? So these are the 3 steps. You do the free body diagram. From the free body diagram, you draw the from the free body diagram, you draw or you write the equations, and then step 3 is solve. Okay. So summary of our lecture today. There are 3 laws of motion. Okay. We will focus on Newton's second law for the most part. Okay. And then utilizing this law uses free body diagrams, equations, x and y, and then solving. Okay. So in the next lecture, what I'll do is I'll talk about, or I'll do examples with, basically we'll start with normal force, then we'll start doing tension, we'll do one-dimensional examples, two-dimensional examples, and then what we'll do is we'll redo those, we will redo that stuff with friction added on top, okay? Okay, so thanks for watching. I hope it was useful, and I'll see you in the next one.